Okay, so we have finished a big block of lectures that I call tools of machine learning. So we studied few libraries of Python. So now we know how to use NumPy, how to use Pandas, and how to use Matplotlib. With all of that, now you have your toolbox full of tools that you can use to tackle basically many interesting problems, including some sort of gathering statistics and so on and so forth. In this course, we will study in the future some tools that we have in scikit-learn. So we will be studying different methods of machine learning, and we will be more working with all that, let's say, objects from scikit-learn. And I will, of course, assume that at this point you know how to use all that NumPy functions, all different, how to plot a graph with Matplotlib, so on and so forth. So I won't be paying more attention to that functions. I will suppose that you already know what to do. But now is a little bit outstanding lecture, because it's like some sort of mathematical introduction to machine learning. So what I want you to say is that machine learning is based on two things. So the first thing is coding. So you know how to code something, and that's really good. The other cornerstone is mathematics. Of course, we don't need the whole mathematics, nobody knows that, but we need some parts of the mathematics. And the parts that we need are mostly parts that contained within, let's say, such subfield as mathematical optimization. Why mathematical optimization? Well, throughout our course, when we will be talking about different methods of machine learning, you will hear from me very often that everything in machine learning, any method, is some sort of minimization or maximization of something. So basically all our methods, whatever we will study, and methods we will not study, so all that neural networks, support vector machines, different trees, so on and so forth, they all are, if you consider them very carefully from the mathematical point of view, everything boils down to the problem of minimization or maximization of something. And with today's lecture, what I want from you, of course, there are many methods of mathematical optimization, and we are very scarce on time, so we have only, I don't know, 2 hours or something. Of course, I can't teach you all the methods in 2 hours, and I don't know myself all the methods. But what I want from you is, I want that after this lecture, you had some sort of intuitive feeling or some representation in your mind of the problems that we are able to solve when using mathematical optimization. So what we can solve, what we probably cannot solve. So, and when I will be performing some sort of calculations throughout different lectures, so for example, we will study some sort, I don't know, support vector machine, I'll start writing some formulae, I will be doing some transformation, doing, and at the end of the day, I will get some sort of new formulae, and I want you, when you will look at them, you will get an instant idea, oh, I know how to solve that. I know the methods I can apply on them and get the result. So that's what I want at the end of the day. So just some sort of grasp of these methods, what are they capable of, and how do the problems look like, so you may want to reduce something else to that form, and you will know that, oh, I can use now different methods, I can call some sort of functions from SciPy optimize, and so on and so forth. So that's the goal. Okay, and with that being said, let's get started. Regarding minimization problems, there are many areas you may want to use them. So statistics, regression, neural networks, industry management, insurance, gambling, and even physics. So yes, if you are doing physics, you will minimize action, and that's basically minimization problem. What kind of minimization problems do we have? Well, the ultimate goal, well, the pinnacle of optimization problems is the general global optimization. It's your goal to find the global minimum of every continuous function. Every continuous function. The problem is that...
Excuse me, is the screen sharing on?
I'm not screen sharing, one moment. Yes.
No, we see the notebook, thanks.
Oh, okay, very good. Thank you. And the problem is that we can solve that. We can solve the global optimization problem. Why can't we solve it? The thing is that function, let's put it that way, any information that we can use to solve optimization problems is, let's say, local. So what it means, I don't know, local or global information. So if you have a function and you say, for example, it is continuous everywhere, that's a global information. You know something about the whole function. If you are talking about some properties of the function that you define at the point or in a small neighborhood of some given point, you are talking about local properties. That can be the value of the function, for example. So very local property. You are given a point, you can calculate the value of the function, and that's very local. The derivative of the function, very local property. That's all what we have. And the other problem is that when we are calculating all these things, we can use only a certain number of, we can do only a certain number of calculations, because we are working in the real world and it takes time to calculate, for example, the value of the function. So yes, you can calculate it one time or 100 times or a million times, but you can't do that infinitely number of times. That's impossible. So that's the problem. You can gather all information about the function. So whenever method you come up with, you can always come up with the function that is so tricky that it tricks your method. So that's the problem. What do? We retreat to some different problems by setting some restrictions on the function that we want to use. So for example, we set a more, let's say, achievable goal of finding a local minimum, and we use a class of differentiable functions. So we get value of the function, we may get, I don't know, some derivative, first, second order derivative of the function, and we want to find some local minimum. Well, it's it's a goal that we can really try to reach. The other problem is so-called convex optimization. Methods that use, let's put it that way, we have a class of convex functions. I will tell you a few words a little bit later. And the neat thing about these functions is that they have only one minimum. So their local minimum will be their global minimum. So that's why in this case we can, of course, hope that we will find the global minimum of the function just because it's the only one minimum it has. And that's achievable as well. And there are some different methods like interior point methods. I won't talk about that in this lecture, but if you are interested in some sort of different methods that really don't look like what we will be getting through in this lecture, you can go to the Wikipedia and check about interior point methods. Well, and you will probably know something new. A few words about calculus. I hope you remember everything that I wrote here. So you have some function that goes from x to r. Here is a Taylor expansion of the function, just few terms. You have definitely seen the first linear term of this expansion, maybe a little bit more, maybe you have forgotten a little bit about the second term. Here is the H matrix. It's called Hessian, so it's a matrix of Hess. That's a square matrix of second order partial derivatives. So every entry of this matrix has a form second derivative of the function f with respect to coordinates, I don't know, some 2, 3, for example. So it's, if that's cell of the matrix 2, 3, then you are deriving regarding second coordinate and third coordinate. In some cases, people use approximation of Hessian, so here it's stated for you. The second thing I want to remind are terms convex and concave. So here are examples of concave function, convex function, and function that is neither convex nor concave. To get a little bit more like intuition about that, for example, here is the concave function. That means if I take any two values, x1 and x2, I will calculate values of the function f x1 and f of x2, and I can draw a line that connects these 2 points. So the function in between x1 and x2, its plot, will all lie above this line, and that's true for any 2 points x1 and x2. So however I choose them, however I draw the line, at the end of the day I will get my function to be all above this line. Similar thing for convex function. So I draw a line, but my function lies below this line. If the function is neither concave nor convex, you will see that some parts of the function will lie above, some parts will lie below, and so on. With concave and convex function, of course, goes a term of convex set and non-convex set. Convex set is the set that whenever you choose any 2 points within this set, so you have this set, you chose any 2 points, and you draw a straight line, so you draw a segment between these 2 points. And this segment, the whole segment, lies within the set. Here is an example of non-convex set, and you see that if I choose these 2 points, I draw the segment, and I see that the part of this segment lies somewhere outside the set. Convex optimization is a subfield of mathematical optimization that basically studies the problem of minimizing convex functions over convex sets. So convex problems are, I guess, maybe the only ones we know how to solve efficiently. Probably there are some new methods right now developing, but let's say if you take some sort of classical methods, they will be mostly suitable for convex problems. So, and for convex problems, we need all these notions of convex function and convex set. So that's why I'm showing them to you right now. One more neat picture, it's hippograph and epigraph. That's if you have a function, you can basically divide your plane into 2 parts. So one part lies above the function and one part lies below the function. Well, not stopping here, but I want you just to know that convex sets have some sort of list of very special properties. So, for example, if 2 sets A and B are convex, their intersection will be convex as well. And if you take 2, let's say, I don't want to say sets because we need addition operations, so we need at least some sort of linear space. So some parts of linear space are convex, and if I take some sort of all possible sums, I will get once more a convex set as well. and so on and so forth. So there are a number of different nice properties that convex sets have. So if you are having few convex sets, you can probably construct some new convex sets from them. And maybe you even know what is a convex hull. So probably you saw that somewhere. So if you are having some sort of two sets, you have some sort of set, you can take a convex hull of that set. Okay, so now about the standard form of a convex optimization problem. So in general, optimization problems are unsolvable, and it's often the case to choose between the precise model that cannot be certainly solved in a reasonable amount of time and a rough model that can be. So you will be probably changing something in your formulae, in your model, to make it, let's say, solvable. And we know some certain classes of models that are definitely solvable, like linear models, convex models, and so on. And convex problems are the ones that we know how to solve efficiently. Okay, about the optimization itself. Optimization problems, you can divide them into two branches depending on the fact whether they are subjected to some additional constraints or not. So depending on that, you can have constrained optimization problem, or you can have unconstrained optimization problem. Here is the standard form of the optimization problem, and at least these formulae I want you to look at because when we will be going throughout our lectures, in many cases I will try to reduce whatever we have when we will start some new method to this form. So if you see something in this form and you know that your functions, let's say, are good enough, you can be pretty sure that we can solve that. So that we can call some sort of function from SciPy, optimize, and so on and so forth, and get some meaningful result. So that's what we will be aiming for all the time throughout maybe all our lectures that follow. Okay, so once again, convex optimization is a subfield in the problem of minimizing convex functions over convex sets. Here in these in these formulae, f, f1, and all up to fm are convex, and functions h1, hp are affine. Function f is called the objective function, so your objective is to minimize it. And and all functions like fi and hi are referred as the constraint functions, so they define our constraints. Function f well has many various names, so it can be called an objective function, a loss function, a cost function, an energy function or energy functional, and so on and so forth. If you are aiming for maximum, not for minimum, you can call it utility function or fitness function. So that all are the names that function f gets, and it's basically the same function. A little notion about these hj. You see that I basically demand that they all are affine. And maybe you may be wondering why I am thinking that they should be affine. This is the problem. This is connected to the problem of the convexity. So if I have some sort of convex set defined by functions f, you see these sign less or equal. So let me draw a little picture for example. So it's just some sort of to give you some sort of intuition about that. So I won't prove anything or so on. Just a simple example to make you feel why do we may want to make all that h functions affine. So here's an example of function f that takes the whole this whole circle. So anything within this circle is taken in. So that's okay for our constraints. So this is some sort of f, I don't know, 1 less or equal some value, some a, I don't know, from x. This is a convex set. So whenever I choose here any two points, and I draw a line, this segment lies within the set. So for any 2 points, so that's more or less obvious. What about if I'll be trying to write some sort of constraint that contains only equality sign? I will get some sort of circle without its interior. So now interior is not included. How do you say, is this a convex set?
No, it isn't.
No. Yes, you're absolutely correct. It's not. Whenever I take any 2 points here, I draw a segment. What happens to this segment? It lies outside the set. Now the set is just this circle without any interior. Why? Because now I want the equality sign. And you see that this set is very not convex. And possibly, if you think for some time, you will probably come up with the idea that if you want this segment, whenever you take some 2 points, you want this segment to fit into this set, you will probably need to make this set look like this. A straight line. If I have a straight line, yes, whenever I choose any 2 points on the line, I draw a segment, I see that my segment lies on that line. So all points of the segment belong to the set. So hopefully now you have some sort of intuition why do I demand from the functions f that are subject to some sort of constraint that they are less or equal than 0. I just demand from them to be convex, but from functions h that I demand to be equal to 0, I demand from them to be affine. The set of points that satisfies constraints is called feasible set. So if x is feasible, that means that all constraints are satisfied. And one more, let's say, parts of terminology, whenever you see these constraints that something is less than or equal to 0, you should think about, let's say, 2 sub-branches. So whether it's strictly less than 0 or whether it's equal to 0. Depending on that, you can say that your constraint is active or not. So whenever you achieve that equality with 0, you say that your constraint is active. Whenever you do not achieve that equality with 0, you say that your constraint is inactive. Okay. Now, what else? Here are some sort of hierarchy of convex optimization problems. Well, no, before, I guess I will show you just one more thing on the whiteboard about constraints. I just want to have you some sort of intuition what's going on and what are we doing. So here is my function to minimize. Without any constraints, that will be unconstrained optimization problem. Good? Yeah. We have some sort of minimum that's here. So suppose I have some sort of method, it takes this function, it considers this function and tells me here is the minimum. Good. Now I'm adding some constraints. Let's add some sort of very simple constraints. So here is a what happens? No. Okay, but here is some sort of message. Okay. Good. Now let's add some sort of constraint. So if I'm adding constraint that I want my access to be within here, now you see that I have a constraint, but is this point of the minimum I have found in the unconstrained problem is still the minimum. This point, is it feasible?
No.
Why?
Constraint.
But this constraint allows this value, so it's feasible. So that's feasible point, everything is okay. So this is the minimum we had before. Is this constraint active?
No.
No. It's not active. So here is an example of inactive constraint. And when we had this minimum, so nothing changed basically. So why constraint is called inactive? Because nothing changed. Now let me add one more constraint. So here is another constraint. I say that my x should be within this border and this border. So here is another constraint. Now where is the minimum considering the constraint optimization problem?
The left border of the constraint.
Yes, absolutely correct. So here is my new minimum. So if I have a good method of minimization, it will give me this point. Now, what about constraints? Are they both active or inactive? How do you say? Or one is active, one is inactive?
The second one is active.
Yes, absolutely correct. So the first one is still inactive. We are within this region. We are not on the border. The second one now is active. We found our minimum on the border of this constraint. So hopefully that gives you some sort of intuitive picture in your mind. How do active and inactive constraints look like? So inactive constraints, they are inactive for a reason. They don't change you anything whenever you do all that minimization. Your active constraints, that's more complicated because they may prevent you from getting to this minimum. They may do something else, but anyway, this constraint is basically restricting you. So that's why it's active. So that's the reason we pay so much attention to active and inactive constraints. So some are basically doing nothing when others are preventing us from getting to some sort of different minimum. Okay, so here is a hierarchy of different optimization problems. I will just really quickly go through all of this and we will move further. Now, so the simplest problems are probably linear programming. I think that you heard about linear programming. So in this problem, everything is linear. So you have some sort of vector multiplied by vector x. You want to minimize that, and you have constraints like matrix multiplied by x is less than or equal to some vector b, and so on and so forth. Very simple. You have definitely algorithms to solve them. A bit more complicated are quadratic programming problems, and as you see here, everything becomes quadratic. Second order cone optimization, we get a little bit more complexity in our problem. And semi-definite programming, you get even more complexity. Formulae look simpler, but that's before the moment you look at X, and that it should be something very special, let's say. And cone programming, once again, we have even more complicated problem, but with a less complicated statements. I will not go through all of them, just some notions that quadratic programming and second order cone programming, it's non-trivial to show that inclusion. So if you are really into all that methods, you may want to check this lecture on YouTube for more details. And here is just some note that I use a little bit different formulation of semi-definite programming than Wikipedia, and here is the note how to transfer from one to another. Okay, here are examples of constrained, unconstrained problems. We already saw that, so I have drawn you a picture. Now you know how do they look like. One more thing, so-called KKT conditions. So once again, we have a convex problem, and we want to minimize some function f subject to constraints, some fi less than or equal to 0. What I want you to show now is some sort of demonstration that is, let's say, half physical, half mathematical. And by this demonstration, I hope that you will gain some insights or some intuition in how all these things work and how all that Karosh-Tucker, I don't know how to pronounce that, KKT conditions are achieved. So here's an example for you. What do I have here? I have some sort of, I have a particle. So here's my particle, this red thing. This particle is in a space with some sort of potential. I don't know, you can think about it like some gravitational potential, or maybe it has some sort of charge and there is another charge at a certain point, whatever. So you have some sort of field in this space, and of course, if this particle feels this field, you may expect that when you leave it free, it will move somewhere to minimize its potential energy. So it has some potential energy, and of course, it wants to minimize this potential energy. If there were no constraints, this particle could get to some point where we have where it will have minimal potential energy. So nothing fancy here. That's pretty okay. So I'm leaving this particle, it moves towards that point. Good. Now let's add some sort of constraints. So these gray lines, these are some sort of level lines of the function f, and I want this function to be less than or equal to 0. So that's my constraint. What do my constraints do? They create some sort of part where the particle can move, and it cannot get outside. So this black line, in some sense, defines a wall which particle cannot penetrate. So you have some impermeable wall, and your particle just gets to that wall, and it cannot move further. Just from physical ideas, you can think that whenever I leave this particle free, it will once again, it will try to minimize its potential energy, but it cannot go through this wall. So it feels this field, it tries to get through, but it cannot. In this case, how do you call the constraint I have? Active or inactive?
Active.
Yes, absolutely correct. It's active constraint. So now it's preventing the particle to get to this global minimum. If I make a very big wall, what now? Is it active or inactive?
Inactive.
Yes, it's inactive. It doesn't do anything to the particle. It just gets to its minimum as it wants to. Now, what I want you to show in this demonstration, please see what happens to the particle when it gets to the wall. It sticks to the wall, but it continues to move. Two arrows you see, that's the arrow that is normal to the wall, and the arrow that shows the gradient of the field that is acting on the particle. So whenever I leave a particle, a free particle in space, it will try to move along the gradient lines of the field. So just from physics, it just tries to move there. Whenever I put a wall, it presses against the wall, and the wall, of course, does some counteraction. And this counteraction goes in the direction of a perpendicular to the wall, so in a normal direction. Now, how do you think, when does this particle stop? So I'm just leaving this particle. When does it stop? So what should happen at that point?
When the gradient is parallel to the normal.
Yes, absolutely correct. So when the gradient and the normal are on one line, because if they are not on one line, you have some component of force that is not compensated. So when you are pressing against the wall, like I'm pressing now against this table, how much I press, the same force table presses on me. So I can get through this table. But if I have some component of the force uncompensated, so if I press some sort like this, I will move along the table just because I have some part of this force uncompensated. So if we have active constraint and we leave this and we give this particle the opportunity to find its minimum, at this minimum we may be sure that the gradient of the field and the normal to the wall, basically to our constraint, gradient of our constraint, they are on the same line. And this can be mathematically expressed as this sort of equation. So we take a gradient of our target function, of function f, we have one vector. We have gradient of our constraint, that's basically our wall, so the second vector. And I write the equality sign, but of course they are just on one line. They are not, let's say, equal. So I add some sort of a quotient. I call it lambda. So I get, and I get this equation. Minus sign here is, let's say, it designates the fact that, first of all, you are pressing against the wall. So basically, your force is going that let's say, let's put it another way. Gradient of the field that is trying to get you through that wall is going one direction, while the gradient of the wall, let's call it that way, is going another direction. So they are directed differently. So if I want my lambda to be positive, I will put this minus sign. So it just captures that fact. So you are not going away from the wall, you are going towards the wall. And here is maybe the most crucial part of the KKT equations, this thing. If you have many more equations, you may write everything as a sum of this lambda I times gradient of fi, and demand all these lambda I to be to be greater or equal to 0. And even more interesting part, before I collect everything into 4 KKT equations, I want to tell you that at this point I was using all that gradients. But it may be the case that if you have some sort of function that does not have a gradient at each point, so it's not a smooth function. But still, in this case, you can use some sort of technique called support lines or subderivatives, and you can still write some sort of analogous equation to the one I have shown you that uses these support lines. But now what changes, it's when you are taking all that sort of derivatives, it may be not, let's say, derivatives, but subderivatives. You will get many of them, and 0 should be, let's say, in that set of values that you will get when you are calculating this thing. It's a bit more advanced thing, let's say it so, but still you can gain some intuition. So for example, you can think about a particle that is sitting here and it's trying to push against the wall, and you can probably think that it can push up to this direction, so to one support line, and then rotate to another support line, or take any intermediate value. So basically, it should be some more or less intuitive for you. So what about KKT conditions? So the one we have talked about, it's a stationary condition, often used. Primal feasibility, that's just condition that means that all your restrictions are correct. Of course, they should be. We have stated problem that way. We just want the solution with that conditions to be correct. Condition of dual feasibility, you demand all your lambdas to be greater or equal than 0. In physics world, that means that you are pressing against the wall, but you are not going from the wall. So you are going towards the wall. And complementary slackness, lambda I fi should be equal to 0. This means that either your constraint is active or your lambda is equal to 0. So whenever you have inactive constraints, or all your lambdas that correspond to that constraints, they all become equal 0. So that's the case. So probably if you think about it for a few moments, you will get the idea why do we have that. So they are in this manner, they are just excluded from the consideration. Okay, so here is some note. I called it, there are a few examples here. I don't want to go through all of them because we don't have so much time, but probably if you will feel confused, you can refer to the notebook and check these examples. Here are examples of unconstrained problem, inactive constraint, so constraint does nothing, active constraint does something, some sort of problems with so-called constraint qualification. So that's when we are transferring to KKT and we are trying to find maximum or minimum with KKT. It's not always possible, so that depends on some sort of different things. I don't want to get through all of that. Just know that we have all that. Lagrangian dual problem. How much I want to omit that, but we will need that. At least for support vector machines, the dual problem will be a very crucial thing to talk about, so I'll need to show that to you. What do we have? Stationary condition. If you remember if you remember whatever I wrote there, we had lots of gradients in stationary condition. Gradient of function, gradient of constraints, and so on and so forth. Many gradients. Why don't we pull this gradient outside? So here is the formula, and we see that I can pull gradient outside. That's a linear operator, so what prevents me to gathering everything down there? And the thing that now is under the action of this gradient is called Lagrangian. It's often designated with the letter L, and it depends on the x and dual variables like lambda and mu. Lambdas and mu's are called Lagrange multipliers or dual variables. So whenever you hear about dual variables, you should refer to that constraint, to that equation from KKT, and you remember that everything that is under the gradient sign, that is my Lagrangian that contains all that lambdas. Now the interesting part. When I take supremum over Lagrangian, it gives back encoding of objective and constraints. So here is my Lagrangian. I am taking supremum over mu's and lambdas. So here it is. And when I'm doing this, you may remember that I wanted all my functions fi to be less than or equal to 0. So if I'm trying to maximize this thing with respect to lambdas, if I have my constraint, let's say, satisfied, so I have my constraints satisfied. So hi are all equal to 0, and my fi's, they all are some sort of less than 0. What would happen? What would happen if I try to maximize over mu's and lambdas? For lambdas, I demand them to be greater than 0. For mu's, I don't demand anything. How do you think? Any ideas? Okay, so suppose, I don't know, I guess, should I draw that on the blackboard or not? Okay, let's go with formulae. So you have fi, this f, let's consider just f1 times lambda 1. So if my f1 is less than or equal to 0, what is the maximal value of lambda 1 times f1 if lambda 1 can be only positive? What is the maximum value I can achieve? Yes, absolutely correct. 0. So I can get to 0, and that's all. So that's everything I can. When hi are equal to 0, well, this sum is equal to 0, so it doesn't matter. So at the end of the day, if my constraints are satisfied, it means that each fi is less than or equal to 0, and each hi is equal to 0. What do I get? This part with hi's is equal to 0 because hi's are equal to 0. Constraints are satisfied. This part, lambda I fi, is equal to 0. Why? Because you just told me when I'm trying to maximize with respect to all that lambdas, and my lambdas are all positive, the maximum I can get is just to get to 0. So that's all what I can. And at the end of the day, I'm just ending up with the function f of x. So this strange construction with the supremum for each feasible point is equal to f of x. For each feasible point. What happens if point is infeasible? Let's start with the simpler part. Let's say sum of these hi's, say h1, is not equal to 0. I'm trying to maximize with respect to mu I, and I have no constraints on mu I. What is the maximum I can achieve? Anything, yes, infinity. What happens if something is wrong with constraints of Fi? So let's say Fi is greater than 0. I am once again maximizing with respect to lambdas. Lambdas are positive. What do I get when I'm trying to maximize? Once again, infinity. So this expression basically explodes for any point that is infeasible. You get infinity. And here is the logic behind so-called primal form. If I'm trying to find infimum with respect to x of this strange construction, of this supremum, I will get minimum of my function. Why? Because it's equal to my function for every feasible point, and it's exploding to infinity for every infeasible point. So that's what I get. Of course, anything is smaller than infinity. So if you are doing some sort of searching for infimum or some minimization, of course, you will throw away all the infinities because any finite value will be much, much better, infinite better. So here is the primal form. And here is the dual form. We are just trying to swap supremum and infimum, and we call that a dual form. Dual form problems, well, they can be different, let's say this way. Some of them may have the same minimum as the primal problem. Some have not. The good news is that we have some sort of examples of sufficient condition to coincide primal problem and dual problem to coincide. So we have some sort of conditions. It's called Slater's conditions. Well, so I guess you should check some sort of other sources or Wikipedia. It's a bit too complicated to get into that right now. But I just want you to know that we have some sort of ability of transferring from the primal problem to the dual problem. That's one thing. And the other thing is that we have, let's say, the dual problem in many cases, it's much easier to solve. It's often easier to solve. That's not some sort of strict rule, so don't expect it to work all the time, but in many cases, it's simpler. It's always concave, no matter what is the primal problem. That's good for us. If F is quadratic convex, duality gap, so-called duality gap, is always 0. It means that whatever you will get with the primal problem, you will get the same thing with the dual problem. Duality gap is basically the difference between what you get with your primal problem and what you get with your dual problem. And you can always show its so-called weak duality that for any optimization problem, what you have with your primal problem, this infimum of supremum and so on, is always greater or equal to what you have with your dual problem. That's almost obvious. Maybe I will show you that just in, I don't know, few lines. Okay, let's write it right here. So what I have some sort of Lagrangian. I won't write all that arguments, so here is just Lagrangian. And I have infimum of that Lagrangian with respect to x. Okay, let's write. Let it be x, whether lambdas, mu's, x lambda mu. Now, can you tell me what sign like equal, greater, less than I should put in here when I have these two quantities? So I have Lagrangian and I have some sort of infimum of the Lagrangian. When we are taking some sort of infimum, we are searching for smallest value with respect to something. In this case, with respect to x. So whatever I take here, so any value I take here, when I am considering this thing, I have already minimized that with respect to x. So I tried to take something smaller. So of course, this thing is always smaller than this thing, just because I took the minimization. So I don't know how to put it into, let's say, some more simple words. Suppose you have, I don't know, many boxes, and in each box you have, I don't know, cats. So this function with infimum, it means that you have taken from each box, I don't know, the smallest cat you have in there. And now you are comparing cats in the boxes, some random cats from the box, with that smallest cat you took out from there. Of course, it will be smaller, so why not? Now, this sign will be not ruined if I will apply a supremum. So if this is true for any values of x, lambda, mu, and so on, nothing bad will happen if I will say that let me consider not any value, but the values that maximize this thing. So I have supremum with respect to mu and lambda, demanding that lambda is greater than 0. And this is still correct. Of course, if this thing is correct for any x, nothing bad will happen if I will take infimum over x's. So if it's correct for any x, it will be correct for the x that minimizes this thing. Why not? And at the end of the day, you have so-called weak duality. So this is a result of considering primal problem. Here is a result of considering dual problem. And you state this sign between them. So you can calculate value of primal problem minus dual problem. You will always get some sort of positive value. And the value you get will be called that duality gap. So that is the duality gap. We are mostly lucky, and that problems that we will consider in our course will in most cases have no duality gap. So that's really good. Okay, some more examples I did not consider. And now we are getting to some sort of more practical part about the functions and so on. How much time do we have?
20 minutes.
20 minutes.
Yes.
Okay, I will tell some things I will tell you right now and some after the break. Okay, so if you are a programmer, you are programming something, you probably heard about the methods of development called TDD, test-driven development. Did you hear anything about that? No?
Yes. When you firstly write tests, then code.
Yes, absolutely correct. So first you are writing some sort of tests. All your tests are failing at the first. Then you write your code, and then you are trying to make your code to pass all of that tests. Let's do something similar with our optimization problems. So before we dive into methods that will solve the problems, let's check out some sort of tests that we can perform on our methods to be sure that they work. A little bit funny, but the simplest function that almost probably someone will. Oh, I have a comment here. Okay. The function that you will be most certainly tested against is first of all just a quadratic function. So you take a parabola and you are trying to find the minimum of the parabola. When you are getting to something more complicated, you may want to use some more complicated functions and check whenever your method, if you are developing some sort of optimization method, whenever it works on that function. So I will show you a few of, let's call it pathologies of the functions that your method will probably need to overcome to be a successful method of optimization. And here is the first example. It's so-called Rosenbrock function. What is the problem of this function, and why do we want to test against it? As you see here is some sort of long valley, and this function has only one global minimum. It's somewhere at the point, I guess, 1, 1 or something like that. I don't remember the exact expression for this function. I guess it should be somewhere at 1, 1. And the problem is starting somewhere here, you should go down to the valley. Your method should get down to the valley and then go through all the valley to the exact minimum of 1, 1. So here how this function looks like in 3D. And this is not so easy as you might expect. Because many methods fail at this point. So some of them take too long to get to the minimum value because the values of the gradients are very small in that valley. Some methods began oscillating. That's the problem as well. So probably I will show you a few methods and some problems. I have something in here, but you should remember that this function is deceivingly simple. It may look, wow, how any method should do that, but no, this function is enough complicated to fail a big number of different methods. You may have some sort of oscillation problem. So here is a Restringian function. It has some sort of global minimum, but due to a heavy oscillatory behavior, you might guess that it's really hard to get to the global minimum without being stuck in some sort of local minimum. Saddle point is nothing like some sort of minimum, at least when we humans look at it. But some methods, for example, Newton method, may get stuck at this point. So saddle point may be a problem as well. Whenever you deal with, for example, some second order methods and so on. Or your function can be very, very shallow. So here is a function of Himmelblau, and you may see that this function is almost flat, and it's really hard with so little gradient to go on search for the real minimum of this function. I'm actually not sure does it have one or more. I guess it has one global minimum and few locals. But once again, I don't remember the exact expression for this function, so that's all what I can. Now, most methods, at least the ones we will be talking about, will be so-called iterative methods. So we have some sort of state at some point n in the time, and we need some function that will take this state and will transform it to the next state, to xn plus 1. And this is one iteration. I have some sort of subdivided these methods into a few classes, depending on the information, or if you read some previously, some more advanced books, you may have heard the word oracle. So depending on the oracle or on the information we have about the function. First of all, it's zero order methods. It's some sort of interpolation methods or Nelder-Mead method. I will show you the Nelder-Mead method. First order methods, it's like a gradient descent, probably the simplest method, but we all love gradient descent and many of its modifications that you have not probably, but I think definitely seen if you have trained at least one neural network. Why? Because you define them in parameters. So you always define which method you want to use for minimization, and you have some number of choices, and I guess I will show you probably today all of them. Well, not in details, but at least list of that methods. Or it may be some sort of quasi-Newton method. That's okay. And we have second order methods, for example, Newton methods and gradient descent with Hessian adapted step and so on. Interesting question for you. When we are dealing with these methods, we are at each step, we basically keep track of state, what we do. And at each step, we need a different, let's say, amount of the information. So at zero order methods just need value of the function. First order need, let's say, value and gradient, while second order need the full Hessian matrix. And now I want to give you a tricky question. So if you are training a neural network, you will be most probably using a first order method. So it's almost certain. How do you think why you will almost certain never see a second order method when training a neural network?
It's hard to compute.
Well, not really. There's another problem. Let me help you a little bit. Think about memory. How much memory do you need to keep track the state of what you are doing?
So in second order, we will need the squared amount of memory.
Yes. For the second order, you need to keep the whole Hessian. So it needs a n squared number of, I don't know, some memory cells. And for the first order, we only need n. And why that's so crucial for neural networks?
There could be a lot of those factors to track. So
if you are having a neural network, you are expecting, I don't know, let's remember the first lecture about machine learning methods and so on. I told you about some sort of parameters inside all the machine learning methods. How do you think, how many parameters are living inside a neural network, a typical neural network?
Depends, but could be a lot, really, like thousands or millions. No?
A very old neural network, AlexNet, very old. So now we have much more modern. Had already 1 million parameters or something like that. So 1 million, 10 to the 6. Using second order method even on that network will demand from you having 10 to the 12 of memory, let's say some cells or some sort of storage. That's too much. If you think about modern neural networks, a lot of time has passed. So probably you will find, I don't know, 10 to the 9 of parameters, or even maybe even more. the time is passing, neural networks get bigger and bigger, deeper and deeper. So now we can expect much more parameters.
GPT-4 has 1 trillion parameters.
Oh, that's perfect. So GPT-4, 1 trillion parameters. That that's 10 to the 12, I guess, yeah? Yeah, so million 6, billion 9, and 12. Now you can imagine what will happen if you will try to apply a second order method on that. 10 to the 24th memory, I don't know, memory cells. That's too much, probably, even for Google, I guess. Okay. Now about methods that use iteration. What do they basically do? They choose a direction, so where do we go? And they choose the size of the step, so how much do we leap? And doing all that steps, we will get more or less closer to the minimum. Okay, I guess I will show you at least now one method, and then we will maybe make a break, I guess. So that will be more or less in time. So here is a Nelder-Mead method, or it's called simplex method. So now we are considering a very specific method. This is a zero-order method. That was actually, for me, when I first heard about Nelder-Mead method, that was like a big discovery. I never thought that anything can make some sort of minimization just basing on the values of the function. So it's very, very strange for me. I'm really excited how these methods are working, because as I told you, we always have some sort of very local information on the function. We can calculate its value at some point. We can calculate some sort of derivative, but we don't have anything else. Let me check one thing. If I have it. Yes. So let me make you some sort of demonstration of why am I so excited. So suppose so suppose we are in complete darkness right now, and the only thing I have is a small flashlight. So that's the one thing I have. And what I can do, I can just, I don't know, look under my knees, and this small, infinitesimally small area, this epsilon neighborhood of me standing there, it's everything I know about everything around me. And that's really interesting how, looking at that, I can make some sort of decision. Where do I move my next step? Look once again, make a decision, make a step, look once again, make a decision, and so on, just with this small flashlight and with that little spot of light, that infinitesimally small spot of light, I am able to get from here to somewhere, for example, to my place here. So that was for me very untrivial and very interesting. How all these methods are even able to work? How do they do that? And it's really exciting to know that they work, they do something. And here is the first method that doesn't even use the derivative of the function, it just uses its values. Okay, so how this method works? So the basic idea is considering some sort of simplex in the space where we want to minimize something. And we make this simplex, let's say, row downhill, probing with its vertices the values of the function and trying to find where is the minimum and where to move next. So what do we basically do? There are a few operations that we can perform depending on the values of the function we have. Operation of reflection. We have 3 points, x1, x2, and xr. We check them, well, what are the values of the functions at of the function at these points. And we can make either reflection by reflecting one point that has some sort of bad value. It's very big. We are reflecting it. We can expand if, let's say, we have reflected something and we see that the function began to go down. So we get some values that are less and less. We can expand that way. So that's why it's sometimes called amoeba. So this triangle is deforming sometimes. Or we can contract. So if nothing works, if if we always get some sort of bad values, they are growing or something like that, we are trying to contract. And the last thing is so-called shrink. If we see that everything we tried didn't work out, we are considering that probably the features of the landscape this triangle is living on are, let's say, too tiny for our triangle. So we are trying to make it a little bit smaller. Here is the algorithm in some sort of diagram. So when do you do expansion, reflection, contraction, and shrink? So here are pictures of all that things. So we are probing some vertex xr. If it's smaller than the x1, we can try to do either expansion or reflection and so on. I will not get into all these details. Why? Because in the workbook, you have a problem to implement Noether-Mead method. So I, let's say, advise you, if you have some time, you may try to implement that. It's really easy. You have all the description in the workbook. So there is stated, so write this thing, that thing, this condition, that condition, so on and so forth. And at the end of the day, you will implement all this diagram and you will get an Noether-Mead method. Instead, I will show you this demo of Noether-Mead. So here is the point where I start. So here is my starting point. The function is very simple, something like minus sine of x minus cosine of y, so nothing very interesting. When I start, I am creating some sort of simplex from this point. So I'm adding something along x, something along y. So here is my simplex. In 2D case, it's just a simple triangle. What happens now? This point is now the highest point of the triangle. Probably to get a better minimization, I want to make something with that point. So let's look what the algorithm does. We can check it once again. So we have reflected, expanded, more expanded, now contracted, now shrink, and we get to the minimum. We can check this in 3D. So here you see our triangle. It's now somewhere uphill. And this triangle will try to roll down the hill to get to the minimum. Let's look at that.
It's hard to see a triangle projector. Could you please start it once more?
Yes. It's a bit hard to see due to coloring, maybe. Yeah, I should have done that triangle green. I'm not sure if I can fix that right now. So now it's down here. Okay, let's check some another function. Let's look at this one. So what is this function? Who remembers? Okay, let's see it in 2D. No, better 3D. No? Rosenbrock function. Let's look how Nelder-Mead can make something of this function. Can we find minimum with it? Let's check out. And here it is, 0.11. So yes, now it's at the minimum of the Rosenbrock function. So Nelder-Mead can solve that. That's good. Here is some sort of quadratic function. So here is once again the triangle in the quadratic function. So here is the 2D view. And you see that Nelder-Mead method once again achieves its goal and finds the minimum of the quadratic function. So this is what we have. So hopefully now you have some sort of intuition. So what happens? Oh, we have something in chat. Oh, okay, good. So hopefully now you have some sort of intuition. So what is happening to all that Nelder-Mead? I'm not getting into all these implementation details. So how do you sort that points and so on? So the basic idea, so you are calculating value of your function. You are sorting them in some sort of ascending order. So your x1 is always the best value. So the smallest value of the function is f of x1. And the biggest value is f of xn plus 1. N is the number of dimensions of the space you are working with. And n plus 1 is because simplex in that space always has one more point. If you are in a plane, your simplex is a triangle. So you have 3 points in two dimensions. If you are in 3D, you will have a pyramid. So you have you will have 4 points to make that pyramid, but you are in 3D space. So it's always once more. And looking at this scheme, you will definitely find how to calculate all that things and how to implement Nelder-Mead method. And probably if you do practice, you have a problem there to implement this method. So maybe you will be willing to try and and do Nelder-Mead on your own. Visualization should be written there already for you, so you don't need to bother with all that plotting and so on. You just calculate points and return every iteration where you are. Okay, so what's with time?
We should make a break now.
Oh, that's great. So now we get to gradient methods, and we will consider them after the break. So, okay, 5-10 minutes.
10 minutes.
10 minutes. Okay, so let's make a 10-minute break. Okay. So let's continue considering different methods of optimization. And at this point, we saw at least one zero-order method, Nelder-Mead method. And I think it's time to get to a bit different methods, to the first-order methods. And I guess the most famous first order method that we know today is so-called gradient descent. So standard gradient descent. Very simple method with a very simple idea. It's you are having a function, and this function is differentiable. So you can find its first derivative. You can calculate the gradient. And you all know from the course of calculus, I guess probably calculus 1 even, that the gradient of the function, it's some sort of vector, let's say so, that shows you the direction where the function is growing. So if you are having gradient, you see the direction in which direction the function is growing. The length of the gradient shows you how much is it growing, and you will probably want to make a step in the opposite direction. So you have a direction of growth, and you want to make a step in the opposite direction where you expect the function to get smaller. So that's very simple. And here is the minimization scheme. So I am at the point xn. I am calculating the gradient of my function, gradient f of xn at this point. Everything is okay. It's a very local characteristic. And I am doing a step in the opposite direction. So that's why this minus sign. Here is some sort of parameter, alpha. It's called learning rate. You have probably heard this term if you have ever done anything with neural networks. So learning rates are everything there. This is basically a parameter that scales you the gradient. So maybe you don't want to make such big steps. You want to make them a bit smaller, or you want to make a bigger step, and so on and so forth. The problem of the gradient descent, well, it would be a perfect method, but it has its problems that are more or less encapsulated in this alpha. So everything is perfectly logical. So we want to make a step in the opposite direction of the gradient. The problem is in the size of this step. If we take alpha too small, you will get a very slow convergence. So you will wait forever before your method will get to that minimum of the function. So that's too bad. Okay, let's make alpha bigger. That's bad too, because if your alpha is too big, you will overshoot your minimum. And maybe it may even happen that you will never get to that minimum. So that is possible. Your method may even diverge due to this overshoot. So it may begin oscillate. I will show you that oscillatory behavior of the gradient descent. It may diverge. It may do something else. So it's very bad. What do we do in this case? We are trying to modify this method. There are a number of different modifications. So here is the table of different modifications. Of course, since the formula is very, very simple, so we only have gradient multiplied by learning rate, these are the only two things that we can modify. And here with ticks are shown which parts of this formula are we modifying. So gradient with momentum modifies a little bit that gradient part. Eta grad, RMS, prop, eta delta modify learning rate. Nesterov method modifies gradient part. And some more recent methods like ADAM, ADAMX, NADAM, AMS grad modify both learning rate and the gradient part. If you see here, the last year is 2018. Well, these lectures were written in 2019, and I was a bit lazy from that time to update this table. but you might probably guess that if in 2019 I was able to find some works from 2018, then right now in 2023, I'll be probably able to find some works from 2022 with some sort of modifications of gradient descent. So almost each year we have some work that considers gradient descent method and finds some way to make it a little bit or more stable and better. Here is some small glossary because all these names, you have probably seen them once again. If you have trained any neural network, there is a parameter. What do you want to use when you minimize all that stuff? And here are some names, let's say decrypted. So AdaGrad is adaptive gradient, RMS prop is root mean square propagation, ADAM adaptive movement, NADAM Nesterov plus ADAM, Ada delta, it's adaptive delta, so on. So the first modification, and probably the easiest to grasp, is the momentum. So instead of depending only on the current gradient to update weight, gradient descent with momentum replaces the current gradient with some sort of velocity v that is an exponential moving average of current and past gradients. So it's some sort tracks its history and tries to show you and tries to use that knowledge to make better convergence. Okay, so here is at least here was some sort of interactive article. Maybe I'll try to open that if that works fine. Nope, that won't work. Okay. Okay, then we get to our demo. Here is a function, some sort of sines and cosines, nothing fancy here. And here I have my point where I start, and these green points show you where do I get with the gradient descent. Parameter alpha is the learning rate of the gradient descent method. So I can change alpha. If alpha is too small, you will see that I need very many computation, and I still cannot get to the minimum. So I would like to increase my alpha in this case to get as quick as possible to the minimum, to the local minimum of this function. That's okay, but we may have, let's say, different problems when doing with so large alphas. Here's an example for you. Let's check this out. This is a simple quadratic function. So x squared plus y squared plus some sort of quotient on times x times y. Here you see when I am changing my initial point, I have, well, more or less good convergence. What would happen if I increase the learning rate? Please look at the picture. So now, do you see what happens?
We are oscillating.
Yes, absolutely correct. So in this case, we are oscillating. So gradient descent is prone to oscillatory behavior. And now let's look at 3D. So here is a 3D, and looking at this 3D, you can probably guess why do we have this sort of oscillatory behavior. So we are overshooting this part where our function has some sort of local minimum. We are overshooting it, and we are oscillating. And this is still good because it still converges. But what happens if I still increase my learning rate? What will happen to the gradient descent? Can you guess?
It could miss the minimum, probably, or never reach.
It will be bouncing from y steep end to the other and never come to the bottom of this bowl.
It will never come to the bottom, and it's even worse than that. I will draw you a picture on the board in a moment, but let me first show you that here I'm still increasing, and what happens?
It jumps out of the bowl. If we were to talk about it in such simple language.
Yes, it explodes. It's gradient explosion, basically. So your gradient grows infinitely. Why does it happen? So let me draw you a small picture just to get some grasp of what's going on. Please note, we are considering a very, very simple function. It's not even a Rosenbrock function. It's just some sort of x squared plus y squared or something like that. It's very simple. And we already have some sort of troubles. So let me consider a very simple function like this. And what I do when I'm iterating, I'm being at this point, I'm calculating, well, actually, I'm being at this point, I'm calculating the value of the function. I can calculate the gradient of the function. How does the gradient go at this point?
To the left.
To the right. To the right. So we have some sort of function gradient. So here is my function. Let's call it f. So here is my gradient f. And now I want to do a step in the direction opposite to the gradient f. And I'm taking some learning rate. That learning rate is too big. So when I do this leap here, I'm overshooting the minimum I wanted to get to, and I'm getting some bigger value of the function. So here's my new point. Now you tell me what happened to the gradient of the function at this point when I have overshooted.
It increased.
It increased.
Oh.
It increased. So when I will be making my next iteration, I'll be trying to get from this point back, going in the opposite direction of the gradient. And what I will get as a result, I will overshoot once again, but I will overshoot even more than I have overshooted here because my gradient has increased. So I'm getting somewhere far away to the right. And here my function will be even bigger, and I will get even a bigger gradient. And when I get even bigger gradient, everything returns to our previous, let's say, consideration. So at each step, at each iteration, my gradient will increase, and I will make bigger and bigger and bigger steps, while at the end of the day, it just explodes and goes out to infinity. So that's what I have. So please be careful. Gradient methods can behave, well, not very nice, let's say so, even for simple functions like this quadratic function. Okay, what can we do? We should somehow modify our gradient. Let's try modifying it with momentum. So here is the formula I'm going to use. You're seeing here V instead of gradient. and it's just some sort of, I don't know, it keeps track of its history. So we are still calculating gradient, but we are calculating some average, some moving average with previous values we already had. And beta is the constant that defines for us how much do we want to rely on the current value of the gradient, and how much do we want to rely on all the previous values of the gradient. So that's what we have. When I'm setting beta to be equal to 0, what do I have?
Probably it will be very slow.
Just think about it. If beta is equal to
0, then we have just the gradient of f.
Constant.
Yes, absolutely correct. So we are back to just simple gradient. So this demo I have showed you, you see that beta is equal to 0. So it was just a simple, plain old gradient. Now let's make beta a bit bigger. What do you see? It starts converging. It starts converging. So when beta was 0, we had a divergent behavior. So what I showed you on the table, you saw that we are always overshooting. The gradient grows infinitely, and this growth of the gradient is basically translated into a divergent behavior when we are just jumping all around the space and we don't even try to get to that minimum point. We are basically getting farther and farther away. But now when I'm increasing my beta, I'm getting some sort of influence from the previous history. And you see that now I have a convergent behavior. Not the best one, we still have some sort of oscillations, but it's much better than if we just diverge. At least we can hope for some result. And I can make this beta bigger and bigger unless I even suppress, at least partially, that sort of oscillating behavior. Of course, this method is not like snake's oil, so you can't expect it to solve everything for you. As you see now, when I'm making beta too big, what happens here? So I made beta a bit too big, so it's no good. Why? What do you see in this picture?
It starts diverging, but on other axis, like.
Well, it still converges, but as you might see, when we had just our plain gradient for a bit too big learning rates, it had some sort of oscillatory behavior, and it was oscillating some sort of perpendicular to this value. Yeah, so we have that function, we have this value, and it was oscillating in the perpendicular direction to that value. Now, when I'm increasing beta, it some sort of suppresses that oscillation, but instead, we have some oscillations along the value. So beta can introduce its own oscillatory behavior into our image of all these methods. Well, it oscillates in a bit of different direction. So you should be aware of that, and of course, don't expect that just adding one parameter will solve all your problems. Well, it never does. What else do I have for you? Here is once again a Rosenbrock function. So you might see how these methods work on that. And of course, you may want to choose wisely your beta and your alpha, because for too small beta, you can have some problems, like once again, some oscillatory behavior and so on and so forth. So here is some sort of divergent behavior. Well, this is this is a divergent behavior, and so on and so forth. So you may have some troubles. Here are listed all that methods from the above with all their modifications. Of course, I'm not getting into details of any of them. We don't have so much time. That wouldn't be so good. But I just want you to look at them and, let's say, appreciate how simple they are. So, of course, you have a lot of math behind these stages. You need to prove some sort of theorems that converges, this converges, so on and so forth. But at the end of the day, when you are getting to some, let's say, practical usage of that method, you only have something like 3 to 4 equations that tell you how do you update your variables and how should you transfer from one step number n, to step number n plus 1. So you might guess they all are more or less simple, and pretty much you can implement any of them just looking at this formulae. Here is some sort of picture that shows you the behavior of all that methods on a little bit of complicated function with number of local minima and so on and so forth. What's interesting in this picture is that I took all the methods that you have, I guess, in Keras. Yeah, let me check it. Yes. Once again, if you will be training any neural networks, you'll be probably working with some sort of framework. Maybe it will be Keras. And if you use Keras, you should know all these methods. You probably have seen them. And now I want to show you how do they behave when you are trying to minimize some sort of function, because most cases you don't see what do they do. So you are putting some neural network into there. There are 1 million or billion of dimensions. And of course, you're not trying to track any trajectory that these methods are pathing on, and so on and so forth. So here's an example. How do they behave and what do they do? As you see on the right picture, they behave differently. Some of them are able to find some local minima. One of them, this red one, what that? Adam. Adam is able to find, I guess, global minimum. While this one tries, I guess, diverge, or what is he doing? I don't know. This green line is doing something really strange. This is an example of what all these methods do, and you might notice that they are not perfect as well. But that's the case. As I told you at the beginning of the lecture, the problem of finding the global minimum for any function is too bad, but it's unsolvable. So we can't do that. We can find some sort of local minimum. That's okay, but we cannot find any. But we cannot find global minimum because we are operating just with some sort of local properties of the function. Remember the flashlight. And we can do that only finite number of times because we are using a computer, and we will not wait infinitely long for a computer to calculate something. Okay, what else do I have for you? Stochastic gradient descent. First order method uses gradient. Very good. What it does, here's what it does in a gradient descent step. Okay, let's avoid the formulae. I will show you better a picture. So here is a data flow in gradient descent, stochastic gradient descent, and and batch stochastic gradient descent. In gradient descent, we take all data set. Well, maybe I should first tell you that what we need function f to have a certain form. And in many cases, we do have that. So consider a function f that is basically a sum of a number of summands, and you want to minimize that. So you basically want to minimize some big sum of something. And in in most cases, you will have that sum coming from some sort of number of data points that you have. So you are having some machine learning method, and you want your machine learning method to perform good on some sort of data set. So you are having a data set, you are loading that into your method, and you are trying to make your method work with that data set. What you are basically doing, you are minimizing some sort of function with respect to some internal parameters that your method has. But as a minimization, the overall function of the minimization in many cases goes something like you are taking your data point, you are calculating result with your machine learning method, and you are collecting all that results for all data points, and then you are calculating some sort of mean value and so on and so forth. So you are applying the same function on each data point. You are adding everything together, and you are saying, so this is how good or how bad my method works. And if you are doing just simple gradient descent, you will need to take the whole data set and to calculate the loss function as a sum for each data point you have. So here is the data flow. It shows you that you take every data point and you calculate everything. But you may come up with the idea that if your data set is very large and it's very long to calculate how your method performs on each of the data points, you may think, well, why don't I just pick a random data point, calculate how good my method performed on that data point, calculate all that loss function that I will minimize, and make some decisions how do I change that internal parameters of that function basing on this result for that random data point. If I do that a large number of times, just due to the law of large numbers, I will be more or less doing the same if I worked with the whole data set each time. And that saves me a lot of time, and that's really good. So it makes all processes much quicker. Or you can be a bit more careful. You can use batch SGD, batch stochastic gradient descent. And instead of using one data point, you can take a batch. So you have a large data set, I don't know, 1 billion of data points. You are saying, well, it's too long for each step to wait processing of all that billion data points. And you say, well, let me take some random 100 data points. That will be my batch. I will calculate my stochastic gradient descent on that small sample of 100 data points. And that will give you basically the result. Okay. So hopefully that's more or less intuitive, or not. Yeah, good. Here is some sort of example. So we are minimizing some function. I'll not get into that. If you want, you can check notebooks after the lecture. So here is example calculating with stochastic gradient descent and with some sort of simple descent, and you get that here is the true minimal value, and SGD needs more iterations than just simple gradient descent. That's expected because you are not considering the whole data set, but just some parts of it. But it doesn't mean that it works slower, because on each iteration, you are just considering a small subset of your large data set. So you are gaining some time with the help of that usage of smaller data set. Coordinate descent may look a bit over simplification, but used in many cases, and we will see that, for example, in support vector machines, we are using for minimization some sort of modification of coordinate descent. I will show you that when it comes time for support vector machines, but for today, I just want to show you how that looks like. And here is basically the picture that should explain you, let's say, everything. So you are having a multi-dimensional space, and at each point of time, you choose some dimension. Here are 2 dimensions. If you are in 100-dimensional space, you choose one of that 100 dimensions. And then you minimize along that dimension. That's all. In 2 dimensions, you see like this sort of ladder-like behavior. So you are still seeing some sort of ladder, and you are going along X, then along Y, along X, then along Y, so on and so forth. At the end of the day, you will somehow get to this minimum. One more example. Don't want to waste time on that because we don't have so much time. Too bad. Conjugate gradient method. Few more examples. How do we do some sort of modification of the gradient descent? Here you see what we do. So we calculate this delta xn, like minus gradient of the function. Once again, we calculate some parameter beta, and we have many methods to calculate that, like Fletcher-Reeves, Pollack-Ribier, and so on and so forth. So you get that. You update the conjugate direction. So you add to the gradient of the function, or minus gradient of the function. You add this term, and this term beta comes from one of these things, and Sn is your state at that iteration. And then you perform a linear search, so you optimize along a certain line. So you have a certain line, and you optimize along that line with possibly some different method, and you find some local minimum along that line. You jump to that minimum, and then you do that again and again and again. So what the idea of this conjugate gradient, I want to show you in the example of Newton conjugate gradient. This example uses sklearn method. So you can find that in sklearn library. And here is how it works. So here I started at some point, and I'm trying to get here to the minimum. The first thing I'm doing, I'm trying to find that conjugate direction that is, let's say, more or less perpendicular to the lines of field we have. So you remember that physical analogy. So we have a particle and we have some field that is pulling that particle towards its minimum of its potential energy. So particle wants to minimize its potential energy, and it's pulled by the field. Now I'm seeing all these lines, level lines of the field, and I'm trying to find some sort of perpendicular to that lines. Now I have chosen this direction, and here the method, it basically draws a line, and it tries to find minimum along that line. So this point where we will jump to has the particle will have the minimal potential energy from all the points along this line. So how do we find it? It basically doesn't matter. So you may use some different method. The idea is that there is such thing we call curse of dimensionality. The more dimensions you have, the worse your method works. So that's it just works that way. So if you have some ability to restrain the number of coordinates, that will be very beneficial for your methods, because they will start working better. Here I am restricting everything to one dimension, so I can be expecting to for any or almost any method to work very well. I have only one dimension. That's really simple, really good. And then I will get this point, and from this point I will continue moving. At this point you might guess how the gradient goes. So I will draw some different line, and I will minimize along the different line. So here will be that different line. And along that line, once again, I use some different minimization method, and I get to this point. And so on and so forth. Very nice method. As you see, converges. Here's one more. Optimized gradient descent with Hessian. I will show you some sort of geometric interpretation of all that things, but the idea is the following. We have a gradient descent. We can find the direction we want to move with the help of the gradient. But we had a lot of troubles with choosing learning rate. So you remember, too small learning rate, too slow convergence, too large learning rate. We even can get to some sort of divergent behavior. So we don't want that. So we want some idea, some clever idea that will make us to choose that learning rate at each step, well, in a way that we don't get all the divergent behavior and we are converging more or less quickly. So here's an idea to use the second order terms to calculate that learning rate. Here is some sort of geometric interpretation for you. So here is the particle at some point in time. So we get somewhere. So here we are. Here we can look at any direction we want. And you see in 3D, you see some sort of slice. So I'm slicing the function. So here is the slice of the function. You see this green line. That's the exact slice of the function. And in this slice, so once again, I'm trying to make the number of dimensions as small as possible. And in this slice, I'm approximating my function around this point with some sort second order. So I'm doing the Taylor expansion up to the second order. What do I get from this? I choose this line along the gradient. You can see an arrow here. So when I'm moving this point, you see an arrow on this point. So I'm choosing this line along the gradient. Now I know that I want to move in the opposite direction. So I want to get out from the points where I have big gradient. And in this slice, I have some sort of approximation of my function, how it should look like. And this approximation helps me to guess how large should be a step so that I can get to the minimum. Let's check a little bit better points. So for example, here I am near the minimum. Here I am getting direction along the gradient. And here in the slice, you see that I have approximated my function. Let's move a little bit here. So you can see that parabola. You see this parabola has some sort of minimum. So I can jump into that minimum and hope that I have found, or that I am closer to the exact minimum I am aiming for. Here are the formulae. Well, they are not so complicated as they may look like. So you are just multiplying some sort of vectors, vector and matrix, and that's all. So Nothing fancy here. Here we can explore that gradient and Hessian descent. And here we can see some problems and some advantages they have. So here is my method near the minimum. You can see that it converges quite quickly. So just a few steps and we are there. But of course, we have some troubles with this method. For example, if you guess from the previous demo, I am approximating the function with some sort of second order. So I am approximating that with parabolas. And it's good if my point is near some sort of local minimum. So I approximate that with parabola that has minimum, and I can jump into that minimum, and that's good. But what if I am near the point that is some sort of maximum? I approximate that with parabola, but this time, if you look into all the formulae, you will see that I will try to make a jump into the point of maximum. So this method, if it's closer to a local maximum, it will converge to the local maximum, as you see here. So here is the peak of the function, and it converges to the peak. And it's not a problem of solely gradient plus Hessian descent. You will see this sort of behavior in many different methods. I have already warned you that even some things that don't look like, let's say, maximum or minimum can still be attractive for all these methods. So we can get into troubles there. So this is the case. Okay, let's check some different functions. What this? A Rosen-Brock function. Here we have it. As you see, it converges very nicely. At least most cases. So if I'm near this valley, you see that it really goes down and converges to the minimum I expect. Okay. Newton-Raphson method. Here are the formulae once again. We have a gradient. We are calculating something. But what I want you to show, this is, first of all, it's a generalization of a Newton method to find zeros of function f. So here is the formula for that method. Now I want you to show a picture. So here is the picture of that method. So here I have a function. Here in blue is my first guess. Let's say I should start my iterations from somewhere. So what I do, I draw a tangent to the curve, and the point of intersection of this tangent with the x-axis gives me the second step of my iteration process. I perform the same process once again, and once again. So here is the way to solve equation f of x equals to 0 when you start from some point. In case you are trying to find out why is it obvious that it always converges, I should warn you that it's not obvious and it doesn't always converge. So sometimes it does, sometimes it doesn't, and well, it's the best we have. But a really nice method, in many cases, it will give you the exact result you want and not in so many iterations. And to get some idea why it's the way it is, so why it is to converge is so, let's say, complicated. I want to give you some sort of interesting question. So let me perform this Newton method on a very simple equation, basically finding zeros of the function z cube minus 1 equals 0. So I want to do that in a complex plane, and I want, let's say, consider this method. Okay, I think I should I should draw something on the board. I'm not sure how to use the thing. Okay, how do I use that?
Yeah, yours and
Good. I want to draw on the board, so I guess I should show you the board first of all. I guess would be fine. Good. This is one of the questions to let's say break intuition. So we may have some intuitive ideas of some things, and I want to show you with this example how wrong they are. So let's start with a complex plane. So here is the complex plane. Here I have something like 1 minus 1 I minus I. And I am considering equation like that cube. Oh, it's not that. That cube equals 1. What are the solutions of this equation in the complex plane?
Three numbers. Like
Yes, it's 3 numbers.
circle.
So we all remember the theorem of algebra, yeah, that tells you that whenever we have some polynomial equation in complex numbers, the number of solutions will be basically the degree of the equation. So 3 numbers. 1 is easy to guess, yeah, it's equal to 1. The other 2 are lying somewhere here, so you can guess it's some sort of triangle, and you have all these angles, I don't know how much, 120 degrees, I guess. Okay, so here are our 3 solutions that we have. Now what I want to do, I want to start some sort of iterative process, and I want to see where does it converge, depending on the point I start. So here is, let's call it root A, this will be root B, this will be root C. And if I am starting somewhere over here, how do you think, where do I converge? I'm solving this equation.
Top
I'm
left.
using Newton method. Oh, sorry, didn't hear.
Probably the top left point. Or... No.
So we'll probably guess that we converge somewhere here. That's what our intuition says. So we will converge somewhere here. And if I start somewhere over here, I can expect that I will converge
somewhere
Bottom left.
Bottom left.
somewhere here, yeah. And when I'm starting somewhere over here, I can expect convergence, for example, somewhere here. And maybe if you think for a while, you can say, well, it seems a little bit intuitive that maybe if I take these points and I draw some line, so all the, and then I draw a line here and here. Maybe I do that in blue. If I draw such 3 lines, I can probably expect that points in this part will converge to this root, and points in this part will converge to this root, and points in this part will converge to this root. Does it seem intuitive to you? So, looks great. But what do we have in a real life? In a real life, we have something like this. the colors in this picture show to which root do we converge. 3 roots, 3 colors, RGB. This thing is called Newton's basins. It's a sort of fractal, and as you might guess, the behavior of our method is much more complicated than we anticipated in the first place. So it's really not so easy to fully understand the behavior of the method, because it's very complicated behavior. So with this picture, I want to show you that not everything that we consider like to be obvious or intuitive and so on is that way, because in some cases we can get into troubles. Okay. What else do I have for you? Some calculations. I don't want to do that. You can do that on your own. Quasi-Newton method. Okay, what's that? I guess now we are getting into second order methods. So second order methods, they use the Hessian matrix, and they use all that second order quotients that we have. These methods are a bit more complicated. Of course, we should have a really nice function, so we should be able to derive it at least 2 times. And as I told you, they need a bit more memory, because if you are just doing each step and you are tracking your gradient, you have n components of the gradient. But if you are tracking the Hessian matrix, you are tracking n squared number of components. So probably it will not always work for you. And here is some sort of geometric intuition behind that method. So here is the point, and down there is the function I want to minimize. Once again, when we are doing all that minimization, this point, it does not see the function. So we have access only to some sort of local properties, value of the function, some sort of derivatives of the function, and so on. But we cannot get the grasp of the overall function because that's too much information. We cannot compute that in any reasonable amount of time. So that's impossible. So what do we do at this point? We are considering the second order approximation, and on the image on the right, you see that exact approximation. This blue line shows you where the point is located. So at this point, I'm doing the approximation. And this approximation looks like some sort of parabola. And here you see this green thing. It's a part of parabola that I have approximated my function with. Of course, it does not look like the function, but locally, it's good enough. One interesting thing to notice for you. So here are eigenvalues I have calculated for that parabola. They define me, in some sense, a form of that parabola. So just some small question for you. Here you see these values. What can you say about the signs of the eigenvalues in the context of our problem?
Non-zero and positive.
They're positive.
And now?
Negative.
Okay. And right now?
Uh,
One positive, one negative.
yeah.
Okay, so probably you were taught about all that eigenvalues and you have calculated them in some sort of course in linear algebra, but I'm not sure if anyone told you what do they exactly mean. So if you have two positive eigenvalues, your parabola is going upwards, so like this. And you see that in the picture on the right. If they are both negative, your parabola is going down. So you have some sort of maximal point, your parabola is going down. If one is positive, one is negative, you're having some sort of saddle point. You see this green surface and you see what form it has. So it's sort of saddle point, this point that is designated with this blue line. So here is basically the meaning of that eigenvalues. So if you have never seen that, please remember these pictures and they will make, let's say, obvious for you their meaning and how to use them for, let's say, minimization or better understanding of some sort of surfaces. Here is Newton method working in, well, using sklearn Newton method. You see the result. Okay, freezes. You may know that Newton methods has its own problems. So once again, it can converge to a minimum, it can converge to a maximum, or it can converge to a saddle point. Even that can be a problem. So yes, it's not perfect, but that's what we have. A few more methods. I will not waste, let's say, time on that. But there is so-called Levenberg-Marquardt method. Here are the formulae. It's a further extension of a Newton-Gauss method. You see this parameter lambda here. Depending on that lambda, if it's very, very small, you are basically transitioning to a Newton-Gauss method. So that will be Newton-Gauss method if you remove this red part of the formula. If your lambda is very, very large, it approximates, let's say, gradient descent. So depending on your lambda, you can get a little bit closer to a Newton-Gauss method, or you can get a little bit closer to gradient descent. That's okay. So, and here is the last method I show you for today. That's trust region method, or let's say methods. So we have many methods. They are called trust region because you may probably have noticed that if I'm approximating my function, I have some sort of model, and this model is correct in, let's say, locally around the point I'm approximating the function. So believing in that model everywhere is not a good idea. And that's why we are implying such thing like a trust region. So I'm saying, okay, I am creating some local model. So I am expanding my function using that linear part, quadratic part, whatever I want. But I'm believing in that model only within some region of some size. So here is the trust region. Here is my model. And in this trust region, I believe in my model. Depending on how my model behaves within that region, because I'll be trying to minimize something, I will be trying to jump into the local minimum of that model, I can calculate how good it coincides with the exact function. And basing on that, I can either shrink or expand my trust region. If my model is really good, I'm seeing that my model works, I will expand. If I'm seeing that my model performs poorly, I will think that that it's not a good idea to believe in that model, and I will shrink my trust region. It will look something like this in a picture. So when you are jumping from point to point, and you are expanding or shrinking your trust region, I mean the region where you trust your local model. And here is the last demo for today. I show you this trust region method. Once again, everything is from sklearn. And you see here a Rosenbrock function. Here it is. And we see in this demo how we move from point to point. In each point, we have some sort of radius. It's the size of the region in which we believe in our local model. And then we do some sort of step basing on that model. That makes things really much better because you are not obliged to believe in your model everywhere and always make some sort of mistakes or just believe that your function is good enough and so on. But you can just restrict your region and say, well, I can build some sort of model, but its model will be not good everywhere. Let me consider some size of the region where it's good and do not calculate anything outside that region. So here is the basic idea. Okay, so now what do we have? What did we consider? So today we had a big lecture on the optimization. We have considered a number of different methods. There are many of them still left in SciPy optimize minimize function. So it has some sort of functions. So you still have there some abilities, some more methods to check. But we have considered a number of them. We have considered some sort of classification based on the order of the information we get. So zero order methods that use only value of the function, while first order methods like gradient descent and different modifications. You will definitely see that if you do something with neural networks. And we have seen second order methods that are more advanced, like Newton method, more quick, but they have their own problems, beginning with the problem of keeping track of all the variables we have, because we should keep track of Hessian matrix, and that's n squared number of parameters. And we talked about a little bit about trust region methods that alleviate some problems of other methods. So you may almost any method to convert into trust region method just by endowing it with some sort of radius in which you trust your model or you don't. And the main point of everything with which I want to stop this lecture is the part that whenever we do any machine learning, we do some minimization or maximization. And hopefully when I will transform all the formulae of that methods into that standard view to which we can apply all that KKT equations, transfer from primal to dual problems, so on and so forth, you'll be already knowing that what we are doing and why we are so desperately wanting to get to that point and transform our equation into that form. So with that being said, thank you for your attention. If any questions, comments, please.
Yeah, I have one question. So I never knew about Nelder-Mead method, and it seems very interesting for me. And I tried to search for some papers that use Nelder-Mead for neural networks and compare it to other optimization methods, but I couldn't find any. Do you know any such papers? It's really interesting. I understand that it requires way more memory, but I'm interested in performance. How good or bad is it compared to like the classic methods used for neural networks?
I'm not sure if you can find that for neural networks. I have never seen that on my own. But if you look into some papers on natural sciences, you can sometimes find usage of the Nelder-Mead method, especially in cases when it's really troublesome to get the derivative of the function. So I definitely have seen some papers on quantum optics they were minimizing. I don't actually remember all the details, but I definitely remember that at some point they used Nelder-Mead method to minimize something there, some function. I don't remember actually the exact setup, but it had to do to quantum optics and even to the Nobel Prize that was connected to all that Bell inequalities. So if you remember all that story with Bell inequalities and Nobel Prize for them, well, if you look into that area and into that papers, you will definitely find some using Nelder-Mead methods, because I have definitely seen few of them. Maybe in different cases you can find as well, but that's everything, let's say, from natural sciences. In neural networks, I have never seen Nelder-Mead. I can't tell you exactly, does anyone even try to use that, or everyone retreats to first order methods? No idea. Anything else?
Could I ask about module? Or
Yes, please, of course.
which terms it would be? Is it like
How much time do you have?
What?
Well, I was expecting that you can handle it in 2 weeks, so
So 2 weeks from now, or from weeks from previous lesson?
from the previous lesson
Yes,
when
yeah.
I
Okay,
was
okay. So
stating
okay,
that model.
understood.
Yeah.
Got it. Yes, thank you.
Of course, if you are almost complete, just some problems, I guess I will give you some more time. But I was hoping the problem is not so complicated, so you can handle that in 2 weeks. That's like, I don't know, if you do that on weekends, you had 2 weekends from that Friday, you will have 2 weekends this Friday, and you will still have 2 weekends after the next Friday. So it's like 6 days of weekends only. So hopefully you can handle that. Well,
Yes.
if you have some troubles with something, you can ask, so maybe we can help you.
Okay,
Yeah, we
thanks.
were expecting it next week, but again, if you have questions or problems, just ask me or Vitaly. And like slight delay, you'll still be okay. But we expect it next week, yes.
Okay. No more comments, questions? Something in chat. Okay, nothing. Okay, then thank you everyone. Have a nice day. See you next Friday.
Yeah. Have a nice day.
Have a nice week.
Thank you very much for the lecture.